Okay, so today I wanted to try to optimize one of our older projects, the one with particle simulations, and the idea is that we are doing. Let me show you like the results. We have this thing, which it's pretty scuffed. It's not really that great, but we can add particles inside, right? And after we reach like you can watch up here, this is like the important part, and after something like 600 particles the FPS starts to go down, so we'll have to see if we can actually improve that, right? And we can reset it, and if you hold space it simulates, and you can stop it by And the other cool thing about this one is I used like some project from Sodding, the one with Raylib.js, this one. Like I copy pasted it, I put my code in here, I think, like just particle simulator, the main file basically. I've changed it a bit, but it's pretty much the same. And it actually worked to run it in the browser. So if you want just to see it, you can actually just open it from this URL here, and it should run. But it's worse. It is what it is. But it pretty much has all the functionalities, right? But the main focus is to basically just add Pthreads on the native build, on the main one. And so I thought that it might be interesting because it's gonna require like barriers and stuff, and a bit of thinking, because you are gonna see we have like some for loops which can be easily optimized. Like there's not an issue to optimize for loops, but we run them like on each frame, so that's where things like require a bit of thinking. How can we optimize running on each frame? That's gonna be the main idea for today. And so let me just open up NeoVim, and let's go into the main file actually, which is main.c. And the first thing, let's just include what's called pthread.h. This is the header file that will provide us with the pthread create functions and stuff like that. Here we need to add another parameter in our program, and this will be the number of threads. Like this is just for me mainly, doesn't really matter. So we can actually add a number of threads, and let's read the value here. So let's leave Copilot do the job. Well, if value is not null, let's make it optional. And if we go in the ini file, we can actually add the number of threads. Let's make it 1 for now. Okay. And let's see. So the function that's causing us some trouble, let's say, is this simulation step, right? And like this is what we want to optimize. So let's see what's inside of it. We have this for loop that calculates the density and pressure, like some classic stuff for particles. Then we have another for loop that calculates the pressure gradient, let's say, and that's mainly the direction where we want to move our particle into. Like we get the direction and like a bit of distance, how much distance we want to move it. And we cannot have a single for loop because here we need to wait for all threads to finish. Like that's one idea. Like yeah, I mean that's the idea basically. We have to wait for all the other particles to compute their densities because the gradient of one particle depends on the values of all the other particles. And the last for loop, I don't know why it looks bad. Now it looks good. Is to remove the collisions. Like if we have collisions with the walls, like you saw with the walls of the simulation, we have to not let the particles go through. So yeah, that's the idea. So we have 3 for loops we can optimize. So let's see. First, let's create. If you are already familiar with Pthreads, we need to create a void pointer function. So this is basically, let's say for the first for loop, let's just call it particle properties thread, right? And it gets a void pointer args here. So yeah, I wanted to say that if you are familiar with Pthreads, you might know that we cannot really send arguments like this, like you send them in Python, where it's pretty easy. We need a structure for this thing. So let's create a structure, struct args, and what are we gonna need here is basically all this stuff, right? Like all this stuff right here. So we need the particles. We can give it the parameters, which will be probably easier, and the start and the end. All right. Let's keep it simple. Let's do it like this. Okay, so here we need to get. I mean, obviously, it should be pretty easy to just copy. Let's just copy paste this and change it based on how it should look in the thread. Right, so we are gonna say first of all we need to convert these arguments into our structure. So we're gonna take the name, put this here, say it's a pointer A, although the pointer should come here, and we need to cast the arguments to this structure. Okay, so yeah, now we have to add a arrow to pretty much everything inside of our for loop. So yeah, okay, so that's everything, and we just need a return null at the end because we don't return anything. Okay, so this is just how you convert a for loop. Well, not entirely true. We need here to use a start and a end. So we, instead of doing the entire for loop, we do just a small chunk of the for loop. So that's the idea. And now we can delete this thing, and yeah, we can create that structure, but we also want to create pthread t. We want to create the threads themselves. So for int I equals 0, I is smaller than params.threads, we iterate the threads. What we have to do is pretty much just initialize the arguments, and I don't really like to do it like this. Well, I mean it's correct, but if I is equal to the last one, let's put also like to have like maybe something like threads per count. But let's leave it like this for now. And yeah, we just create the threads, and but I mean we can use a variable like int particles per thread, and it's gonna be that thing. And here we can use particles per thread. Oh, I mean it's the plural, so particles. And then we have then we have to join the threads. So now I mean CMake. I don't think we should notice any difference, to be honest. I mean probably it's gonna be worse if you think about it, because we have to spawn a thread on each frame. So yeah, that's gonna be probably worse. So let's try to add something like 16 threads. Let's see if this improves in any way the so it still starts to drop at around 600 particles. Maybe it's a bit faster. We got like 700 particles and it's 30 FPS, and before it was like around 600 and it was 30. So maybe it's a bit better doing it like this. But as you can see now, what we would have to do is do it the same for this for loop and then for the last for loop. And the problem with this is that well, here we spawn basically 16 threads, then spawn again another 16 threads, and again another 16 threads. So it would be what, 48 threads, and we can do better than that actually. And the idea is, what if we put everything inside of this function? But first let's just visualize how that might look like. So I think we can reuse this thing and the arguments. Yeah, I don't see why not. So I guess we can reuse those. So let's have here another void pointer particle gradient thread void pointer args. Let me see. Because I think this is the same, so we can just rename this in particle thread args, just to be more generic. So we're gonna need this thing, and let's copy paste this for loop. So as you can see, again we need to go through all of these things, make it work with the new structure. We need the delta time though, so we can actually just add it, but it's like, I mean, just code it here, like probably it will work. whatever, and here we just return null, right? Okay, so instead of this entire for loop, oh yeah, again I forgot to use a start and end. So yeah, again, instead of this for loop, let's do a for, and let's leave Copilot do it. It looks good, and the Pthreads join. So this one I think it should also work, but again, we might not see a really big improvement. Let's see. Well, it actually improved quite a lot. We're still at around, wow, it's almost double, even more. But I think like now it's failing because of the maybe relief or something, I don't know. So even if you go faster than that, it won't matter. But you saw that only this small change actually improved the simulation quite a lot. And yeah, now let's see. For the first one, it's the same thing. For the last one, I meant. So void particle collision thread, and let's leave Copilot do it. Collision thread. I mean, maybe if I did void pointer, let's see. You got it. I mean, from the examples above. So yeah, even this one, I saw that here I used get frame time anyway. So yeah, let's do another for loop here. Let's leave again Copilot handle it because it's just copy pasting. And yeah, this should still work. Still works, and yeah, the only issue is that we, like right now it works with 600, but it starts to, I don't know why it starts to flicker at around 1500 particles. Maybe it's too many particles to handle on the GPU or something, like in drawing them. But yeah, we get to like 40 FPS. Anyway, so now, yeah, you saw that we pretty much sped up the entire thing from 30 FPS at around 500 or 600 particles to now it gets to 40 FPS at 1500. So it's much better, almost triple the speed, like what's it called, the speed up. It's like a 3 speed up, 3 times. So like this kind of speed up is pretty decent, but the thing is we can do even better than that, right? So right now if you look at the code, we create a thread here, then also here, and also here, and we do that 48 times, like 3 times the number of threads, and I put 16 threads. So it's like we do that too many times, in if I'm being honest, because we can do better than that. And the idea is, what if we put, like what if we combine all these 3 functions? So instead of the like what all we have to do is just delete this, right? Delete this part, and now we have a single function. Alright, so this will be particle simulation. What? Particle, is it called like simulation step? Particle simulation step thread. So let's see what happens if we do this thing, right? If we do this thing, so instead of doing everything else here, let's just have that. So basically we have the same thing as before. We don't need this tt. We have the threads, the arguments, the number of particles per thread, then we spawn the threads. We do particle pthread create, right? And then we stop the threads, and we do that on each simulation step. And yeah, in this function we do a for loop over this chunk of particles. We calculate their density, then over the same chunk we do the gradient, and then again on the same chunk we remove the collisions. So let's see what happens if we do it like this. Like, oh, where did the particles go? Well, the issue with this is that here we don't wait, like before, when we start this for loop, we don't wait for all the other threads to finish their density computations, right? So we have to wait. Here we need to wait for all threads to finish, and the same thing is done here, right? We need to wait for the other threads to finish, and only then we can start working on these chunks pressure gradient, and the same thing for removing the collisions. So we can do that by using a barrier, and let's see how we can create one. So pthread, or what's it called, barrier, pthread barrier. I don't like that it imports the thing. Anyway, pthread barrier t, and we are gonna have two barriers actually. One here, or maybe we can reuse the same one. I don't know, we can try to have two barriers. Well, I mean, let's see, sync barrier, sync. I mean, it can be called barrier, and that's it. Okay, so then the next thing is to initialize this barrier. So pthread barrier init, and this function gets the number of threads basically, because how the barrier works, not gonna do drawing, I mean, yeah, it stops the current thread until all the other threads are also at this point. And how does it know that all the other threads are at this point is to use here the number of threads. Or like maybe if you have some more complex logic, you can put less than the number of threads for some reason, if you need only some threads to be synchronized or something like that. But yeah, usually here you'll put the number of threads. So that's initializing the barrier. And now how can we use it? Well, you put it in the arguments. So pthread barrier, we put it in the arguments. And let's send it, and at the end, I guess after the join, we can destroy the barrier. So now we have the barrier, so we can actually say barrier and well, I mean, it's arrow barrier, and I think it's weight. But I don't know why I don't get the completion. Because I'm trying to program in freaking JavaScript. Pthread barrier, and we can do weight. Okay, so yeah, basically here we wait, and then again I think we can reuse it here. So let's see what happens now if we try to run this. Well, you can see that now it actually the particles don't explode, and we actually get them. And let's see if 1500 is again a point where the FPS drops. Yeah, I mean, somehow, no, not really. I mean, yeah, it's pretty much the same. It's almost the same. It's more like 1600 or, yeah. But, I mean, it's close. But, like, it's a bit of an improvement, I would say. Right, like, we, instead of having a single thread for each for loop, for each chunk, we have one thread for all of them. And, yeah, we use barriers to synchronize the for loops, right? We use barriers. But I mean, I guess we can do even better than this. Like, what if we don't, let's say, spawn a new thread on each like iteration of because if you take a look at simulation step, it's called on each frame. It's called inside this while true loop, so it's called on each frame. So what if we create all the threads outside of the update loop, and yeah, basically have this pthread create be called only once, and that might improve things even more. So yeah, let's see. So instead of saying, but we need to make a small change to our argument structure. So instead of having start and end, let's have thread index basically, and we have to compute the start and the end based on so particles per thread. We get the particles per thread, and then we get the start, end, and if we are on the last thread, we get everything. So yeah, we make a small change here because the start and end can change based on the number of particles, and this worked because it was inside of the update loop, and we can pre-compute the start and end. But when we do it outside, we are no longer able to pre-compute the number of particles, right, in some way. And I would say the same thing for the params. We might need a pointer to the parameters. Let's do something like replace params and then dot with params arrow, and let's not really all of them. I wanted to do it just for this function, so we can actually do it like this. We select and say params, and we change it with params arrow. Oh, I should have used the G for that to replace everything basically. So yeah, and if we put G, it does it for all of the stuff. Okay, get pressure params. We can dereference it here, and remove result collisions. Also, we can dereference it. Doesn't really matter. So yeah, now here we need to pass the address of the params. Basically, that's the idea. So yeah, now instead of using simulation step, we will have to use the simulation step thread. So let's change the name, simulation step thread, and let's see some other stuff we use in our thing. So we have this is key down basically. So for this one, I would copy this with key is press space, and inside our thread, well, the idea was to compute everything just when this key is pressed. So yeah, let's see, because we have, it might I was thinking it might make more sense to have another smaller function that will wrap around this, because it's it's gonna be too large. So it's not gonna be simulation step, it's more like particle simulation thread, right? And it should get the same arguments, so it should get, still it gets A as the arguments, but inside of this thread, so we can actually, let's not delete that yet, but it should have this for while loop, anyway, for loop, while loop, the same thing. So it has this while loop, then basically if key down, or what's it called, space is key down, if we have a key down which is space, we should call to this thing basically. So and here we can pass in args. So this is how I was thinking to do it. And another obvious thing is we need to also sync the particle simulation step on every frame. So one way to do it is to just add another barrier here at the bottom of the function. Right, just wait for all of these to finish, and only then we go again. So that's the idea, to have like this small wrapper function, because otherwise we would have to paste everything inside and it looks a bit ugly. So yeah, let's go ahead and take everything from here and let's move it in the main function. So that would be like after the init we have all of these, right? Then the next thing would be to create. So we no longer need that, but we need all of this stuff. So let's see. After we initialize the window and set the target FPS, well, the barrier can be initialized there. Okay. Particles is what? We need to take the address. So we need the particles, the parameters, and here when we use the address, I think that if the particles change, since we are on threads, I guess it shares the memory with the main thread. If the particles change, I guess the entire argument will, like this will also change, right? Because it's an address. So that's what I'm thinking. And here we don't spawn a single step, we spawn the entire simulation, right? We spawn this thing with a while loop. Okay. And then at the end, after we, well, I guess it could work here, but I'm not sure. I guess it doesn't really matter where you put it, right? So yeah, like again, let's see. So we create these threads. We create all the threads beforehand with this particle simulation thread. And now instead of calling simulation step here, we can actually delete this function, right? We have these threads that run on their own and they have that body here. So if the key down is space, then we can do a single step on a chunk, and we do basically density, then we wait for all threads, then we do pressure gradient and wait for all threads, and then do collision and wait for all the other threads, and then again on the next frame we start again. So I think everything should be working fine, but it doesn't. I wonder why is that. So let's do some printfs. Let's see if I was right about index. What about the number of particles? Well, I guess it's easier to just show all of them at once, because it's gonna be a dot index. I mean, that's gonna show it once. I would like to see it on every step. So it's, but see, it increases, so that's fine. Wait, what? Yeah, now we have to figure out why that happens. So if we go inside of the ini and only use one thread, this shouldn't have any problems because it's like a single thread, but it still does have some issues. So I'm really curious why that can happen though, even with a single thread. Yeah, pretty strange why that happens with a single thread. Particular simulation. Because yeah, I would expect maybe it's somehow interfering with begin drawing and stuff, which could happen. But yeah, like maybe trying to sync these things. So let's say we add another barrier that will try to sync the while loops, because maybe that's the issue. So let's create another barrier, pthread barrier t, and this should be maybe main barrier or something. And here we need to pthread number of threads plus 1, because it's also going to be the main thread. And what if before begin drawing well, I would still say that we have to wait on the main barrier. Then we need to add the main barrier in this thing, pthread barrier main barrier, and inside of the while loop we have to wait the main barrier. So this will block here, right? This will block here, and on the main thread it will block it. Where was it? It will block it here before begin drawing. So all the computations, like all this stuff, all the logic, will have to finish on all threads, even the main thread, and only then we can start drawing. And should we do anything else? Like maybe have even another barrier after the drawing. Maybe we need another pthread barrier wait at the end, and that means we have to put just another barrier wait here, which just one after the other. And let's not forget to put the main barrier inside of arguments. Let's see, because I think this should synchronize also the drawing. So for one thread it works fine, and let's see, yeah, again at 600 it goes down. So that's just the so yeah, this actually fixed it, right? I guess, because we are waiting for the logic to finish on all threads. We do synchronize for the logic, so all the threads will have the same FPS. It's what I'm thinking. So it waits for that, and then it also waits for the drawing to finish before we can start the logic again. So yeah, I think that should actually fix it. To me it looks pretty much the same, but oh my god, it didn't work on that one. So another idea is, let's add another barrier. Let's say maybe the order is important. Right, so let's have a barrier here before a key is pressed space, and on the main thread that barrier should come here. Right, so basically here happens update particles, right? That's why we have two barriers. We update the particles. Here we update all the key presses and stuff. Then we wait on all threads. We update the particles. We wait again on all threads, and we draw the particles. And so here we draw particles. And before this one is key presses on main thread or something. Let's see. Because it's clearly some issue with... Okay, seems to work. Because it was clearly like an issue with synchronizing the arguments, let's say. Because maybe when we were creating new particles, maybe okay, and we can see that it's almost the same as creating Pthread on each frame. Maybe the compiler does some optimizations on that one, but we get to around like 2000 particles until it gets to everything goes to shit basically. Yeah, I mean, anyway, like a small number of particles looks better anyway. So yeah, I guess adding more barriers fixed the issue. And now this thing runs on multiple threads. So yeah, I guess wasn't that difficult to achieve this. And basically what I was trying to say about the synchronizing is that maybe we were changing the number of particles, right, when we were clicking. And what if one of these threads started to run already, but we were in the process of clicking around, and basically one thread had a different count here, and they had overlapping start and end indices. Basically that was the sync problem. So when we added this barrier here, we solved that. Basically what we are doing, like on a higher level, if you think about it, is we have I mean, this can even be drawn in a GIMP. Why not? I have to do my daily dose of drawing, so this would be, let's call it main, right? And these are the other threads, or something like that. Let's imagine it. So in the update loop, how it runs is first we run the main loop, getting all the key presses, updating all the particles. So I don't know, it's like input. Then we basically run all the other threads. This is updating particles, updating all the particles. So this here is a barrier. Then we have another barrier. Then we have the main thread running again, and this is basically the GPU, putting everything on the GPU, and then another barrier. And then start again with the input, then the update, and the GPU. So that's why I have 1, 2, and 3 barrier weights, because we need to synchronize like the order of these operations. We cannot really have these two overlapping, this and this, and maybe we could have these two overlapping, but it might produce some artifacts because the position of the particles is not done yet. So for maybe for one frame it will be wrong, but for the next one it's fixed, something like that. So it's maybe better to just have this barrier here. And then again we need another barrier here, just because if we wouldn't have it, then yeah, what would happen, I guess? I mean, probably we don't even need this, because yeah, what if we try to remove this one? Let's experiment with it. So let's remove this, and also this one. Let's try to see what happens, because I think we don't need it. Yeah, I think we don't need it, because that's well, I was actually not able to close the window. So what would happen if we don't have it? That's a good question, and I don't really have the answer for it. Maybe the issue is, let's say, so here we basically go back, right? So what if the main thread is like somewhere random, and if we press escape, it tries to close the window, right? It puts this variable to true, or I mean false, whatever it is. And what if our threads are stuck on this barrier? Right, so they wouldn't be able to see this window should close, I guess. But if they are stuck on this barrier and we press escape, the next time they will be free to go again, we'll find that this is in fact true and will exit. So that's why we actually need that barrier. I mean, it's good to experiment and see if was working without. It's good that we figured it out pretty fast why it was important. So yeah, then we have all of these joins and destroys. Oh, we need another destroy for the main barrier, and I think we are good. So yeah, I mean we didn't add too many things, just a number of threads. Here we did like Pthread stuff. We also added the default argument, and yeah, we just changed this to work on chunks. Instead of from 0 to 1, we work from start to end, right? And we have this separate thread that runs the simulation logic. We have a separate thread for that. I mean, multiple separate threads. Okay, with like barriers to synchronize everything. So that's another thing that we did. we touched on the barriers and why they are useful, basically for synchronizing. And yeah, I mean, not that many changes. And the improvements were at least like on 600 particles, we still have 60 FPS. So that's what I basically wanted. See, like it doesn't even flinch. Even though, yeah, I mean, it still looks weird with all the particles on the border, but yeah, we can still change some of the parameters, see what happens. I mean, maybe increasing the density helped. Let's see what happens if we, so right shift, if we change the gravity. With zero gravity. Let's try to increase the density. Oh, I mean, that was the maximum I set, 3.5. Yeah, I mean, wow. I have no idea, I think I pressed R or something, yeah. But now we can have more particles. Like maybe, let's say, 3 times as many particles, and it still runs smoothly. And I think this is, I mean, still doesn't work to close it, so maybe I lied. Yeah, if you try to close it while you run the simulation, well, probably I didn't rebuild it. Am I right? Yeah, I didn't rebuild it. So, no, I would have been like, what the hell, how does it not work? Okay, so yeah, it works to close it. Okay, so, yeah, basically, this is the result of today. We can add more particles. Yeah, and that's everything. I mean, the web version still doesn't, will not have that because it's, I think it would be way too hard because we would need to implement everything from scratch. But yeah, so we have this thing, feature, add Pthreads to main app, whatever. So yeah, I mean, hopefully you learned something new from this one, and yeah, I'll see you on the next coding day.